temperature dependence of the rate of a reaction. See, most of the chemical reactions are accelerated by increasing in temperature. Example, the decomposition of the dinitrogen pentoxide, the time taken up for half of the original amount of material to decompose, that is 12 minutes. 12 minutes in at 50 degree Celsius. 5 hours. 5 hours at 25 degree Celsius. Then 10 days at 0 degree Celsius. See, already we discussed in the practical, that is volumetric analysis, potassium permanganate versus oxalic acid. The temperature range when you heat that mixer, nearly 60 to 70 degree temperature means the reaction will proceed faster. Otherwise, the reaction is very slow because of the carbon dioxide present that reaction. So, when the liberation of the carbon dioxide gas 60 to 70 degree Celsius temperatures mean the reaction proceed faster. So, that is also one of the example. See, it has been found that the for a chemical reaction with rise in the temperature by 10 degree, the rate constant is nearly doubled. So the temperature depends on the rate of a chemical reaction by accurately explained by Arrhenius equation. The Arrhenius equation is K is equal to AE power minus EA by RT. So this is called Arrhenius equation. Here the A is the Arrhenius factor or the frequency factor. It is also called pre-exponential factor. Then it is a constant specific to a particular reaction. So R is a gas constant, T is the temperature, EA is the activation energy. So the activation energy joule per mole. The unit is joule per mole. It can be understood clearly using the example like hydrogen react with iodine to form hydrogen iodide. See, hydrogen gas react with iodine gas to form hydrogen iodide gas. So this reaction, hydrogen, so the atomic molecule then react with iodine to form intermediate, like see the intermediate like this, hydrogen iodine, then this is the intermediate step, then to form hydrogen iodide and the hydrogen iodide, that is the 2 moles of hydrogen iodide. So that according to the Arrhenius theory, that is the reaction can take place only when a molecule of hydrogen and the molecule of iodine collide to form an unstable intermediate. This is the unstable. It exists for a very short time and then breaks up to form 2 molecules of the hydrogen iodide. Okay. See, look at this diagram, potential energy versus reaction coordinate. The energy required to form the intermediate, already we seen that reaction, that is called activated complex. So this is known as C, the symbol, activated complex, that is activation energy also called, this is the activation energy EA. So by applying the plotting of the potential energy versus the reaction coordinate represent the profile of the energy change when the reactant change in the product. This is the reactant and this is the product. Okay, some energy is released when the complex decomposes to form product. So the final enthalpy of the reaction depends upon the nature of the reactant and the product. Next, all the molecules of the same reacting species do not have the same kinetic energy. So since it's difficult to predict the behavior of any one molecule with precision. So Boltzmann and Maxwell used statistics to predict the behavior of large number of molecules. See, according to them, the distribution of the kinetic energy may be described the plotting of the fraction of molecule versus the kinetic energy, that is fraction of molecules Ne by Nt. Here number of molecules energy, that is E, and Ne, then total number of molecules, that is Nt. Okay, so this is called the peak of the curve. Look at this, the peak of the curve correspond to the most probable kinetic energy. So that is the kinetic energy is maximum fraction of molecule. There are decreasing number of molecules with energies higher or lower than the value. So when the temperature is rise, the maximum the curve moves in the higher energy level. See, this is the temperature. Higher energy value, that is the curve broadens out. Look at this, the curves broadened out, that is spread to the right such that there is a greater proportion of the molecules with the much higher energies. So the area under curve must be constant, since the total probability must be 1 at all times. We can mark the position of the EA, that is the Maxwell Boltzmann distribution curve. This is the Maxwell Boltzmann distribution curve. So increasing the temperature of the substance in the fraction of molecule with colloid with energies of greater than EA. So it is clear from that this diagram, the curve is the T plus 10. The area of showing, that is T plus A, the area of showing the fraction of molecules having energy equals to or the greater than the activation energy. So it gets doubled, leading to doubling the rate of the reaction. Then already we know that the Arrhenius equation. The Arrhenius equation, that is the factor is E power minus Ea by RT. That correspond to the fraction of molecules that have the kinetic energy greater than Ea. So taking the natural logarithms of both sides, you will get, that is ln k is equal to minus Ea by RT plus ln A. So this equation having that plot, that is ln k versus 1 by t. This gives a straight line according to the equation, that is the Arrhenius equation. It has been found from Arrhenius equation that the increasing the temperature or decreasing the activation energy will result in an increase in the rate of the reaction and an exponential increase in the rate of constant. That is, the slope is what here? Slope is minus Ea by R, and the intercept ln A. Intercept equal to ln A. So we can calculate the activation energy using A, that is A using value, that is at temperature T1. At temperature T1, that this equation will be, that is ln K1 is equal to minus Ea by RT1 plus ln A. For temperature, at temperature T2, ln K2 minus Ea by RT2. So this into ln plus ln A. So this one equation and this one equation. So here, since it is the reaction, that is A is a constant for a given reaction, so that the K1 and K2 are the values of the rate constant, the temperature of the T1 and T2. So subtracting the equation this and this, you will get, that is 1 and 2, you will get ln K2 minus ln K1 is equal to minus Ea by RT1 minus Ea by RT2. So further simplifying, taking of ln the same, that is ln K2 by K1 is equal EA by R into 1 divided by T2 1 divided by T1 1 divided by T2. So converting of ln to log, you will get that is log of K2 divided by K1 is equal to EA divided by 2.303 into R, then you will get that is T2 minus T1 divided by T1 T2. Okay. So this is called Arrhenius energy equation calculating for energy activation. Effect of catalysis. Catalyst is substance which increase the rate of reaction with it, that's mean without itself undergoing any permanent chemical change. Example, this 2 moles of potassium chloride KClO3 in the presence of manganese dioxide catalyst MnO2 to form 2 moles of KCl and oxygen, 3 moles of the oxygen. The word catalyst should not be used when the added the substance reduces the rate of reaction. So the substance is then called inhibitor. So the substance is called what? Inhibitor. The action of the catalyst can be explained by the intermediate complex theory. According to the theory, a catalyst participates in the chemical reaction forming temporary bonds with the reactant resulting in the intermediate complex. Okay. This has a transitory existence and decomposes to yield product and the catalysis. So it believed that the catalyst provide an alternate pathway or the reaction mechanism by reducing the activation energy between the reactant and product. So and hence the lowering the potential energy. See, look at this diagram. Lowering the potential energy barrier. This is the barrier. This curve reaction path without catalyst. This curve indicates reaction path with catalyst. Okay, this is energy activation, that is energy of activation with the catalyst. This is energy of activation without catalyst, and this is the reaction and this is the product. So it is clear from that Arrhenius equation that lower the value activation energy, faster will be the rate of the reaction. So a small amount of the catalyst can catalyze the large amount of reactant. So a catalyst does not alter Gibbs energy, that is delta G. The delta G of a reaction, so it catalyzes the spontaneous reaction but does not catalyze non-spontaneous reaction. So it is also found that the catalyst does not change the equilibrium constant of the reaction, rather it helps to attaining the equilibrium faster. So that is, it catalyzes the forward as well as the backward reaction to the same extent so that the equilibrium state remains same but is reached earlier, that is faster. Next is the collision theory of the chemical reaction. The Arrhenius equation is applicable under the wide range of the circumstance. The collision theory which was developed by the Max and the Williams, that is William Lewis in 1916 and 18. See, this theory provides a greater insight to the energetic and the mechanistic aspects of the reaction. So it is based on the kinetic theory of gases. According to this theory, the reactant molecules are assumed to be Hart sphere and the reaction is postulated to occur when the molecules collide with each other. So the number of collision per second per unit volume of the reactant mixture is called collision frequency. Simply denote Z. That is collision frequency. So the another factor which affect the rate of the chemical reaction is called activation energy. That for a bimolecular reaction, that is A plus B gives products. So the rate of reaction can be right the way, that is rate is equal to Z of AB e power minus EA by RT. See here, this ZAB represents the collision frequency of the reactant A and B, and E exponential factor, that is minus EA by RT, represent the fraction of the molecule with energy equal to or greater than the activation energy. This equation, comparing with Arrhenius equation, we can say that A is related to the collision frequency. So this equation predicts the value of the rate constant fairly accurately for the reaction that involves atomic species or simple molecules, but for complex molecules significant deviations are observed. So the reason could be that all collision do not lead to the formation of the product. So the collision in which the molecules collide with sufficient kinetic energy and the proper orientation, so as to facilitate breaking of bonds between the reacting species and the formation of new bond to form the products, are called effective collision. For example, the formation of methanol from bromomethane depends upon the orientation of the reacting molecules. Look at this. See, the bromomethane, that is methyl bromide, react with the base. Improper orientation gives the no product, and the proper orientation gives the product with intermediate. This is from an intermediate. That is, the proper orientation of reactant molecules lead to bond formation, whereas the improper orientation makes them simply bounce back and no product is formed. This is no product is formed. So to account for the effect of collision, another factor, that is P, called probability or the steric factor, introduced. So it takes into account the fact in the collision molecules must be properly oriented, so that rate is equal to P is at AB e power minus EA by RT. Okay. So this collision theory, activation energy and proper orientation, the molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. Okay. Thank you, students.